Now, let me summarize the topics that we studied in this course. So, we started with the introduction to optimization problems, where we saw that optimization has lot of applications in science and engineering. So, many problems in physics can be solved using optimization techniques. Similarly, many problems in engineering can also be solved using some of the optimization techniques. Now, most of the practical optimization problems are constraint optimization problems, and as we saw in this last few lectures that the constraint optimization problems can be solved using unconstrained optimization ideas. So, after seeing some mathematical background on matrices, vector spaces, we moved on to study convex functions. In many applications, convex sets and convex functions play an important role, and one good point about the convex functions is that there is no problem of local minima. So, we saw that for convex functions every local minimum is a global minimum, and the set of solutions form a convex set. So, we discussed about the convex sets, convex functions, and how to check the convexity of twice differentiable functions, and then we studied the theory of unconstrained optimization. In particular, we discussed about the first order necessary conditions and second order necessary and sufficient conditions. We also saw that for unconstrained minimization of convex functions, the first order necessary conditions at optimality are also sufficient. Now, after studying this theory of unconstrained optimization, we studied some of the methods those could be used for solving unconstrained optimization problems. So, we started with the steepest descent method, and then studied Newton method, quasi-Newton method, and conjugate gradient method. Steepest descent method uses only the derivative information, while the Newton method uses the second order information. Now, we also saw that Newton method requires the inverse of the Hessian matrix to be computed at every iteration, and which is computationally expensive. And further, Newton method may not converge from any starting point. So, then we discussed about quasi-Newton methods, which approximate the inverse of the Hessian by a positive definite matrix. So, the quasi-Newton methods do not use the second order information directly, but for quadratic functions we showed that when the iterations terminate, the Hessian of the original objective function would be the inverse of the Hessian of the original objective function would be obtained at the termination. We also studied conjugate gradient methods in this course. So, we saw that for all the optimization methods, it was important to ensure different conditions to achieve global convergence. In particular, if we start from an arbitrary point and make sure that there is at least a constant decrease in the objective function at every iteration, and the sufficient angle descent condition is satisfied, then the optimization algorithm would move closer to the optimal point, or in the limit it will go in the vicinity of the optimal point. So, we saw this global convergence theorem, and also we discussed about the different rates at which different optimization algorithms converge to the optimal solution. We then moved on to study the theory of constraint optimization. In particular, we considered a general linear program of the type minimize fx subject to the some inequality constraints and some equality constraints. And we saw the Karush-Kuhn-Tucker, or in short KKT conditions for the optimality of the given constraint optimization problem. So, we also saw the first order and second order necessary and sufficient conditions for an optimality for an optimal point of a given constraint optimization problem. Similar to the unconstrained optimization problems, for the convex programming problems, where the objective function is to minimize a convex, where the objective is to minimize a convex function subject to convex constraint set, we saw that the first order KKT conditions are necessary and sufficient. But this may not hold for a general nonlinear programming problem. We also saw that when we talk about the constraint convex programming problems, the first order KKT conditions are sufficient only when the Slater's conditions are satisfied. So, for other general nonlinear programs, under the regularity assumption, we saw that the KKT conditions are sufficient. The second order KKT conditions are sufficient. We then discuss about the duality theory. Duality is a very important concept in optimization, and we saw that many problems which are difficult to solve can be solved very easily by solving their dual problems. In particular, we saw some examples where the number of variables is very large and the number of constraints is small. So, in such cases, it may be a good idea to convert the original primal problem into the dual problem and then solve the dual problem. Now, we also saw some conditions under which the solution, optimal solution of a primal problem and the optimal solution of a dual problem are same. So, in such cases, if we are not going to lose anything by solving the dual problem, and if the dual problem is easier to solve than the primal problem, it may be a good idea to solve the dual problem. The dual functions also have some advantages. In particular, the dual problem is a convex programming problem irrespective of the original primal problem. So, when we discuss the theory of convex optimization, we saw that there is no problem of local minima as far as convex optimization is concerned. So, one can utilize this fact and the fact that sometimes the dual programs are easier to solve to write the, so these facts can be used to convert the original primal problem to the dual problem and then solve it. And under certain special conditions, the optimal primal and the optimal dual values are the same. We then studied linear programming. So, in particular, we saw how to use Keketi conditions to design an algorithm to solve a linear program. Now, the simplex method, which has been very popular to solve linear programs, was also discussed. So, we used the Keketi conditions to find out the incoming and outgoing basic variables, incoming non-basic and outgoing basic variables at every point of iteration. One important thing about linear programs is that the solution lies at the extreme point of the feasible region. So, it is enough to search through the set of extreme points to get a solution, and simplex method gives us a systematic way of moving from one vertex to another and find an optimal solution. Now, the simplex method has some drawbacks, like in some cases it may have to search through all possible vertices to find a solution, and the number of vertices could be exponentially large in number, and therefore, simplex method or simplex algorithm is not a polynomial time algorithm. We then saw some of the interior point methods that could be used to solve a linear program. So, in particular, we saw the affine scaling method and Karmarkar's method. So, Karmarkar's method uses a projective transformation to convert the original linear program into an equivalent program, and under certain assumptions, that equivalent program can be treated as a linear program. And the idea of this transformation is to get a reasonable improvement in the objective function. And if this procedure is repeated at every iteration, try to transform the given point xk into the y space to get yk such that yk is close to the interior of the close to the center of the feasible region, and then take a step in the steepest descent direction. And if this procedure is repeated, Karmarkar showed that this procedure will have a polynomial time algorithm which is much better than Khachiyan's ellipsoid method. We also saw a variant of Karmarkar's method, and that is the affine scaling method, where the transformation used is different than the one used by Karmarkar. Although this affine scaling method is simple and easy to implement, it is not a polynomial time algorithm, but it was a very simple method to study. So, we saw that method. Now, after studying linear programming and then the associated dual problems, we studied some of the algorithms for solving constraint optimization problems. Now, there exists plenty of techniques to solve constraint optimization methods, and we have chosen only a few of them in this course. So, the techniques that we discussed were active set method, penalty and barrier function methods, then augmented Lagrangian method, and cutting plane method. Active set methods are very simple and easy to implement. So, the idea is that at every iteration given a feasible point xk, we find out the set of constraints which are active and solve the optimization problem with respect to those active constraints. Now, the solution of this optimization problem may be either within the feasible region or may be away from the feasible region. So, if it is within the same, if it is within the feasible region, we find out the new set of active constraints. Otherwise, if the solution was outside the feasible region, we ensure that the new point is brought back to the feasible set, and then at that point the set of active constraints is found and the same procedure is repeated. Now, if the objective function is convex, then one can show that if every time we are going to decrease the objective function, then this procedure will terminate in finite number of iterations, because there are only finite combinations of active constraints for a given problem. We also saw the penalty function and the barrier function methods. The idea is that instead of minimizing the problem fx subject to some constraint set, one can define an auxiliary function using either a penalty function or a barrier function and solve an unconstrained optimization problem. Now, the idea is to use a sequence of auxiliary functions and solve the corresponding unconstrained problems at every iteration, and if we repeat this procedure, you will get a sequence xk of optimal x's for every objective for every auxiliary function, and these xk's would converge to x star as the iterations progress. So, that is the idea of penalty function methods or barrier function methods. The barrier function methods are similar to the interior point methods, which start with a feasible point and then ensure that at every iteration the point remains feasible. So, at no point of time the barrier function methods let a iteration point xk go beyond the feasible region. On the other hand, the penalty function methods start with a point which need not be feasible and then slowly bring it towards the feasible region as the iterations progress. Now, both these methods do depend on the parameter c, and as c goes to infinity, these methods will face some numerical difficulties. So, we discussed the idea of augmented Lagrangian methods. Now, these methods use a perturbed optimization problem and estimate the optimal value of the Lagrangian multipliers at every iteration. So, the idea is very simple and can also be extended to the inequality constraint problem by writing the inequality constraints as equality constraints using a new set of variables. So, if you write the inequality constraints as equality constraints and then solve the problem, the augmented Lagrangian methods are very useful. And we also saw finally the cutting plane methods, which are very useful and which solve the approximate dual programs because the original dual problem is a infinitely constrained linear program. Now, all these methods are very popular and the choice of the methods depends on the problem at hand. So, this completes the discussion in this course. I hope this course contents were very useful. Thank you. I also would like to thank the NPTEL staff for their assistance. So, thank you very much.